So, welcome to afternoon session. And the first speaker is Matteo Mucciconi from National University of Singapore. And his title is Raw Taylor Derivations for the Stochastic 6-vertex model. So please.
Okay, thanks. Thanks for the invitation, and really welcome back from lunch. And I will present you the talk titled Lower Taylor's Deviation for the Stochastic 6-vertex model. It's based on 2 articles with my collaborators. Sayan from Chicago, well, he's from India, but he's staying in Chicago right now, and Yu Chen, he's from China, but he's staying in Michigan. And it's based on 2 articles. One is been published, and the other one has been we posted on the archive in July. So the title contains the word the stochastic 6-vertex model, but we have already heard these vertex models, about vertex model, for example, from the talk by Philippe. In my case, I am more humble. There's only 6 vertices instead of 20. Okay, it also contains the word stochastic, unlike in the previous case. So let's see what this model is about. First, let's look at the definition, and then we cover some brief history. The stochastic 6-vertex model can be thought as a probability measure on ensembles of paths that we take on a square grid, for example. We can think this lattice to be infinite in the left and in the right direction, but okay, for simplicity, let's consider finite lattice. So this is a probability measure. Let's give, instead of giving a general definition, let's provide a simple way of sampling such an ensemble of paths. The ingredient that you need is a series of stochastic moves, that are written in the table here on the top. But let's see how to use them. We consider a grid like this one, where we take arrows that are entering always from the left boundaries, and from the bottom boundaries we take no arrows entering. Then we imagine for the moment that the grid is empty, and we want to populate this grid with paths following some random rules. The way to sample this path configuration is the following. We start first from the bottom vertex, and the path is entering, and the path has to decide whether to go upward or to keep going straight. The decision is made based on the stochastic rule prescribed here. For example, this path here will go straight with probability given by this number here. I think this is very small. So this is a series of numbers depending on 2 parameters, A and Q, and they are all between 0 and 1. So with a certain probability, which is 1 minus A divided 1 minus A times Q, the first path is going to go straight, and with probability complementary, which is A times 1 minus Q divided 1 minus AQ, the path is going to decide to go upward. Okay, we have sampled the first vertex, then we sampled the vertices on the diagonal just above. For example, this path here is going to, now we know that this path went to the straight, so the path here is going to decide either to go straight or to go up, knowing that no path is coming from below. So the random rules followed by this path at this location will be the same as the one that we just described. Similarly, the path here is going to go straight or up following similar rules. So we keep updating the configuration of the paths, where at each new update we consider a diagonal. For example, this is the diagonal x plus y equal to 5, where new paths enter at the new location above, and we sample the random moves of the paths moving downward. It is clear that this is a stochastic Markov dynamics, and that well, it is clear. Maybe it is clear that this is a Markov Markov chain on this on the configuration of paths, and we can continue updating this configuration for arbitrary times. Okay. Let me know if there are questions. Maybe I'm not clear. So the ingredients that we used is okay, the boundary conditions, which we took to be deterministic, and which all paths entering from the left and no path entering from below, and a series of stochastic weights, which depends on the arrow configuration, and which are called W. These are analogs of the stochastic or of the vertex weights, which we have seen certainly last week from Michael, and earlier from Philippe, for example. The stochastic six-vertex model can be interpreted as a model of of a random growth by interpreting the paths as edges of a certain random staircase. Imagine that you are here and you are at height 0, and you want to travel in the left up direction, and whenever you meet a path, you think of this path as a step of a staircase. So this creates a height function, which we see here. For example, here we have a 0. We cross one path, we have 1. We cross another path, we are at height 2. We cross another path, we are at height 3, and so on. And so this model of paths becomes rather naturally a model of random growth. One can see the stochastic elementary weights interpreted in the language of height configuration. And these are two completely equivalent formulations of the model. Okay. Another way of defining the height function is putting yourself at location mn and counting the number of paths that you meet by going straight downward until the x-axis. So this model was first introduced by Gua and Spohn, 1992, which they used to this model is solvable by Deviations, for example, and was introduced by Gua and Spohn, where they used the solvability structure in order to derive a 1/3 exponent. But yesterday, I learned that actually a similar derivation was done slightly earlier by Dar. I was told, but as it was mentioned before, the notes are in some obscure Indian, library. So I didn't know this, but okay. So Gua and Spohn introduced this model, but probably the same calculation. Dar probably did not introduce the same model, but he concluded similar results by Gua and Spohn. Okay. So recently, this model was made popular and solved even further by Borodin, Corwin, and Gorin, which they used the Bethe-Hunter solvability to derive law of large numbers and a certain version of the central limit theorem for this model, for the 1-point fluctuations of the height function. So in the last 10 years, okay, it's not yet 10 years, but in the last 10 years, many results have been achieved. For example, the law of large numbers, as I said, fluctuations, stationary measures have been studied and are actually a current object of study. For example, in various geometries, when you vary the nature of this lattice, maybe you take a cylindrical lattice, maybe you take a lattice which has boundaries, like discussed earlier by Tomohiro. So why is this model relevant? Okay, it's very simple to sample. It describes an interesting physics, namely the physics of the KPZ universality class. But from an algebraic and solvable model point of view, this model is essentially the building block of every other exactly solvable model, because playing with these rules, one can define many other exactly solvable models. For example, the asymmetric simple exclusion process, the certain models of directed polymers, although it's not obvious to see this from this definition, but it's log gamma polymers, for example. These are popular directed polymer models, they are in one dimension. They are a particular case of this model here. Zero range processes like the one described yesterday by Rouven. Random walks in random environment, KBZ equation, and so on. So if you have a good control of this model, then maybe you can extend your knowledge. You can specialize your knowledge to all of these other particular cases. Okay, but we don't consider particular cases today. We consider this simple case, stochastic 6-vertex model. The law of large number is written here. So we consider the height function at a certain location, which maybe n is the height. Okay, this is actually a square. So n, the size of the height and the size of this side here is the same, but n is the height, and we look at a certain location, alpha n, here. We look at the height function, which I recall is the number of red paths that I meet going downward. This number of paths grows linearly with n, and the growth is given by a certain parameter, mu alpha, which is written here. It's 1 minus alpha here. It's 0 if we go eventually to the right, and it has a non-trivial shape in the middle. Maybe some of you noticed that the model actually depends on another parameter, which is q, but the dependence on q is not visible from the law of large number. Okay, so the law of large number is explicit, but in Borodin, Corbin, Gorin in 16 did something more, which is to derive a central limit theorem for the fluctuations of the height function. So if we center the height function, subtracting the mean, and we rescale by a standard deviation, which in this case depends on q, and we check the probability that this number here is larger than s. So this quantity converges as for large n to a function f2, which is the f2 of minus s, which is the GUE Tracy-Widom distribution. So the GUE Tracy-Widom distribution describes the fluctuations of the edge of the spectrum of large random matrices. In this case, it has a minus sign, so the figure is reversed. Here is the PDF of the Tracy-Widom distribution.
Matteo, is the theorem about fluctuation valid for any alpha or just alpha in the range?
The fluctuation?
It's for all alpha?
Only in the liquid region.
Only for this?
Right, thank you. For alpha in the liquid, otherwise there is basically no fluctuation. If you look here, so this model, like I said, has been studied recently. A major result came earlier this year when Agarwal, Corwin, and Hegde proved that the joint law of this process converges to the KPZ fixed point, among other things. The result is actually more stronger than this. But okay, we just for the purpose of this talk, we just need we are actually not going to talk about fluctuations because we care about large deviations. So moving to the discussion about large deviation, let me focus on the Tracy-Widom distribution. So large deviation events are events that go beyond ordinary fluctuations. So for example, from this plot, we see that the probability that the height function is larger than its average, although we see that this random variable here is peaked to the right of the origin. Actually, the tails here are extremely small, much smaller than the one on the left. Okay. So this comment should shed some light on the nature of the large deviations. Let's focus on. So there are two. If we look at the height function, there are two types of large deviation regimes. Well, there are only three possibilities. No, the height function grows as usual, as following the law of large number. The height function grows smaller than the law of large number, or the height function grows larger than the law of large number. So growth processes have the property that the height function, so the tails of the fluctuations are not symmetric. So the event that the height function grows more than average and the event that the height function grows less than average, they have different decay. Let me show you why. Let's consider what is usually called upper tail. So the upper tail is slightly, in a slightly unorthodox way. Upper tail means the probability that the height grows less than average. So let's consider a situation. How can we realize a situation where the height function grows less than average? So the height function here is the number of paths to the below. So basically we have to construct an event where we have a few paths below a certain point. If you interpret these paths as trajectories of particle, we understand that in order to create such an event, we have to force a single particle to not move or to move upward. If a single path moves upward, then this is going to force all of the other paths to, this is going to force on all of the other paths a certain drift upward. So this heuristic argument says that the decay of upper tail rare events are exponentially small with rate e to the minus n and a certain rate phi plus, which I call here, because this rare event can be caused by a single path having a typical behavior, right? Imagine ASEP. If you want to force the current of ASEP to be smaller than average, you just block one particle, and all of the other particles to the left have nowhere to go. The situation are different when it comes to the complementary regime, what is called to be lower tail, the probability that the height function grows much more than average. In this situation, the decay is actually the decay of this probability is much higher. It decays as e to the minus n squared. And why is that? The reason is that in order to create an event where more paths actually go to the right, so the height needs to be much larger, meaning that if I look below, I need to see more paths than on average, then this can only happen if an O of n distinct paths have atypical behaviors, right? So these lower tail events are much more, much more unlikely to happen and also much more difficult to study. But this is this is the result that I present today. So the lower tail of the KPZ equation were solved. So this is some related works. So for the case of the KPZ equation, which, like I said, is a special limit of this model, they were solved. Well, they were first studied by Corwin and Gosal, where they obtained certain sharp upper and lower bounds, and subsequently solved by Li Cheng-Tsai, Cafasso and Claes in 2022. There are also further works in physics literature, and recently in the other paper that I mentioned before, we consider the lower tail rate function of a similar model, which was probably contained in the question before in the previous talk when Takashi said that there is a certain deformation of the polynomial model connected to whole little polynomial, and this is what it is. So more on the other probabilists have considered similar problems of lower tail. For example, in recently this year, Setsuraman and Baradan studied the lower tail large deviation of the ASEP, but in a slightly different situation than ours, when boundary conditions, which in this case we take to be deterministic, in their situation were random, Bernoulli boundary conditions. In this situation, the decay of the lower tail is actually the same as that of the upper tail. The situation drastically simplifies when initial conditions are random rather than deterministic. So this makes the study the lower tail much more complicated. Okay. Okay, the situation of having different larger tails, depending if we look at events where a random variable grows larger or smaller than its average, are common in random matrix theory, and they were studied by these authors. So let me present the main result, myself, Sayan, and Yuchen. So this is slightly difficult to read, but the result is this. So consider a number S contained between the law of large number of the 6-vertex model and 1. Then the limit of the logarithm of the probability of that the height function grows larger than S times n, divided by 1/2 squared, converges to a certain exact function, which I called phi minus alpha S, where S denotes where we are denotes the event that we are considering. Okay, so this is the limit. So there exists a rate function, and yeah, the height function, the 1-point height function of the stochastic 6-vertex model, satisfies a large deviation principle. So more on this function phi. So this function phi is non-decreasing, non-negative, convex, and has several other properties. First of all, at the law of large number, the value of the rate function is 0, as usual. So the probability that the height function is larger than the law of large number should not decay. Well, at least should not decay exponentially. So this is fine. When we consider the probability that the height function is larger than or equal to n, so this event is, if we go back, is exactly the probability that all of the paths fly to the right. Which means that it can be computed explicitly, because you basically have to compute the probability of the partition function of a vertex model, which only has one configuration. And from the definition of the vertex weights, it can be argued that it can be seen that this is the value of the rate function. In the bulk, so between these two values, between mu alpha and 1, the rate function can be written in this form as the supremum of the difference between two functions, a function f alpha, which I'm describing below, and a parabola. The operation of taking supremum of difference of function is actually common in convex analysis, and it's called infimal deconvolution. You can think of this as an analog of the deconvolution for in analysis. So let's discuss the function f alpha. So the function f alpha is given here. There are some constant factors, and then there is a function f alpha here, lower, I mean, not this other alphabet, where f alpha is the infimum over a certain class of function phi of a functional I, which is written here. This is a log gas because of this logarithmic term, and the potential in this log gas is given by this function here. Of course, I'm not expecting people to actually pay too much attention to all of these formulas. What I want to stress is that the potential here is C0 but not C1. So this is an important fact. That so usually if you open a book, for example, the book by Forrester or the book by other people, the book by Forrester is actually called log gases, so very relevant when studying this problem. But all of the theorems that you find start with take a potential which is at least C5 or C3. In this case, the potential is C0 but not C1 because we have a minimum function. We have a piecewise linear function. Okay, so this function f is itself convex, is C1 but not C2, and is asymptotically a parabola. Okay, so these are a few information that I described. So this theorem appears to be quite complicated, and the reason the theorem is complicated relates back to the fact that lower tail events needs to be slightly complicated to analyze. And in fact, it's almost a miracle when the function f alpha here has a fully explicit expression. In the case of the KPZ equation, the rate function actually has a fully explicit expression, which allowed substantially the analysis. In our case, we don't possess an explicit expression. We only have its characterization as a minimizer of a certain energy of a logarithmic gas or log gas, and so makes our analysis more complicated. So the proof of this theorem includes 3 ideas, which I want to enumerate in the following 24 minutes. Wow, it seems like a lot, 24. Okay, 3 ideas. One is a certain a priori property of the rate function, which actually turns out to be a logarithmic concavity property of the probability distribution of the height function of the stochastic 6-vertex model. Later, I will introduce how to relate the height function of the stochastic 6-vertex model with the log gas that appeared in the theorem, and finally I will state a inverse Varadhan-like lemma, which is going to allow us to conclude. I will explain hopefully in detail what all of these words mean, because we are among integrable people, so maybe some words are not common. Anyway, so let's take a look at the first idea. The first idea is actually a bound, which might be of independent interest, which is written here. Now, preparing this slide, I realized that this is much too complicated. So this is the philosophical version of this inequality. This is a logarithmic. Imagine that the probability that the height function is larger than a certain number. Take this function as a function of r. Then, as a function of r, this function is midpoint logarithmically concave. So if you take the logarithm, you recognize the convexity, midpoint convexity. Okay, but if you don't take the logarithm, this is a midpoint logarithmic concavity. So the word logarithmic concavity, since we have time, appeared recently because in 2022, Junha, for example, was awarded the Fields Medal for proving, among other things, unimodality or log concavity of certain sequences in for example, algebraic geometry, but other contexts, combinatorics. This is because of the connection between the 6-vertex model and symmetric polynomials. This is an instance, not unproven. But this equality here is only philosophical. This is not what we proved, but I believe it's true. But anyway, this is an instance of one of the log concavity results that could be proven potentially with this certain new advances. But okay, I don't discuss this. I discuss this inequality. So compared to the logarithmic concavity that I stated in the previous philosophical slide, we have error terms. We have a diverging term here, the divergence with a certain constant times m times n to the power 7 of 8. Okay, this is just this is a non-optimal estimate, and also inside this function here we have a correction term. Okay, so what does let's go back to the philosophical statement. What does this log concavity property tells you? This log concavity property tells you that for example, that Okay, it tells you that the tails of H are log concave, but log concave probability distribution decay exponentially. So this could be thought as a statement of tightness. One can probably use this statement to prove, for example, a law of large number. So what is the most log concave distribution is the Gaussian, for example, that concentrates around the mean. Well, okay, so this is a small correction. Let's take a look at the proof. So okay, there is a big problem because you can never see what's written here. But the proof is, I will show actually better slides later. The proof is graphical. It amounts to create a certain coupling between pairs of height functions. But this coupling can be realized through pictures, so I'm lucky. So let's take a look at this proof. So what we want to prove, okay, let's take a look at what we want to prove. We want to prove that the probability, that this product of probability is smaller or equal than the probability. Okay, let's actually state what we want to say. We have the probability that the height is larger than R1 times the probability that the height is larger than R2 needs to be smaller or equal than the square of the probability that the height is larger than the midpoint between R1 and R2. Okay? Okay. The way we prove it, like I said, with some pictures, but let me comment first that if this was to be an equality, some people among you might be thinking, okay, there must be a bijective proof. Okay. But since it's an inequality, maybe there is an injective proof, right? So, Arvind is laughing. And this is exactly the philosophy with which we used to prove. So what we need to do, we need to take two height function, one which assume, let's say, value R1 at a certain position Nm, and another that assumes another value R2 at the same value, at the same location Nm. Starting from these two functions, I want to construct another pair of functions in which both of these functions assume the value R1 over R2 divided by 2, the midpoint, right? And I want this mapping to be injective. So here's the mapping. So we start with our two height functions. We consider their overlay. We place them on top of each other. The blue surface is going to be, well, not globally, but locally around the point Mn that we are considering is going to stay below. Now we lift up the blue surface by R1 by the midpoint of the difference, half the difference that separates the two functions at the point where we are interested. Now we have that the height function, the blue height function is over the orange height function in most places, but not in this location here. So what we do is we flip the height functions at this location. You see this orange island has become a blue island, and this blue island below has become an orange island. So we flip the value of these two height functions. Now the blue height function has a problem that had been lifted, so we have to bring it back. We have to shift down h prime, which is the blue height, by the same amount that we shifted it up before. And this is our mapping. We started from a pair of height function, h and h prime, with the property that h prime assumes the value R2 here, and h assumes the value R1 here. After we did all of this transformation, we found a pair of height functions that both take value R1 plus R2 divided by 2 at the location Mn that we are considering. All of these transformations are injective, so this is an injection. But there is a problem that this injection does not preserve the probability, because when we flip, the probability, I mean, there is the coupling here is not really, I mean, when we flip, you might imagine that certain vertices, this is the height function connected to a vertex model, so certain vertices change their nature, right? and this creates some errors that we have to keep track of. And here is this is the reason why there is an error term here. In principle, this error term could be arbitrarily large, could be maybe a fractal. So we have to ensure that this error term doesn't grow like n times m. And therefore, we have to allow a certain margin of error in how much we want to get these surfaces close. So this is a proof of, okay, this is a picture, but you can make this into a rigorous proof of logarithmic concavity. But I will come back to this idea later. Okay, what we have established so far is that the height function satisfies, even before taking any limit for any fixed discrete value, satisfies a certain logarithmic concavity property, which basically states that it's the probability mass function concentrates around a value. You can imagine this statement stated like this. Okay, now we need to go back to the original scope of relating finding the rate function, and this is going to come through a non-trivial identity due to Borodin, and then you can also find it in Borodin-Olshansky, which connects the height distribution of the stochastic six-vertex model to the average of a certain observable of a certain probability measure. Let's unpack what's written in this yellow box. Here we have the probability of the height function on the left-hand side plus two quantities, S plus Xi. S and Xi are two random variables which are independent of each other, and they are also independent of the height function, and they have the following nature. S is actually a Gaussian, and Xi is a geometric random variable. The important part is that the tails of the Gaussian are quadratic, and the tails of the geometric random variable are exponential. On the right-hand side, we have this expectation. Let's first understand what is this measure. This measure is the Meixner ensemble. The Meixner ensemble is an instance of the Schur measure, which was briefly defined before by Tomohiro. And it's a measure on a certain set of points, L is a set of points, L1, L2, L3, living on the positive integers. And this is the probability distribution of this set of points. Quite complicated if you have not seen it before. So to make your life easier, I drew here a graph. So if you sample the Meixner ensemble, you're going to see a number of points. You can take the empirical density of this number of points, and this is what you see. The empirical density is given by the blue curves. You can see it's piecewise linear because I sampled finitely many particles. But you see in yellow, you should see the limit shape, which is an explicit curve. Okay, so this should explain. Okay, let me also say this expectation is some expectation which is a multiplicative, in the sense that you only have to, is a multiplicative function of the locations of these points L, J. There will be n points, so we have to take the product for j going from 1 to n, and then there is a constant inside the expectation, which actually doesn't depend on the process. It could be brought outside. So this matching between the stochastic six-vertex model height function and the discrete log gases is actually an instance of a more general correspondence, which was found by Borodin first, and also studied by Borodin-Olshansky in the same, basically the same day. They posted 3 papers on the same day. It's quite hard to understand which come first, but okay. We gave a bijective proof, basically through the tools described in the previous talk, and more recently this type of identity, or the identity discussed before, they are equivalent. Jimmy He and Michael
Matteo, where is the dependence on M in your Maxner measure? I don't see it. Big M.
Sorry, right, good observation. I actually am pretty impressed. I don't know how you see it. M minus 1, and there is alpha n here, and alpha n is supposed to be M.
Okay. Thank you.
Impressive, right? So, yeah, there is a dependence. Jimmy He and Michael Wheeler are giving formulaic proofs, actually also of generalizations of the identities that you have seen before proved with the technology of the box and ball system. Okay, so, and similar matching, essentially similar nature of matching were used to derive the lower tail large deviation of the KPZ equation. In that case, the model appearing here is not the Meixner ensemble, but is the Ayyer process, the Ayyer point process, which is a continuous model, making the analysis much more explicit. If you are a person that has dealt with similar problems, you understand. If not, it is what it is. So,
Matteo, may I ask a question? In the talk this morning, there were shown connections between the periodic Schur measure and Q-Whittaker or Littlewood.
Yeah.
And here, the right-hand side should be obtained as a limit of a periodic Schur measure?
The right-hand side is a special case of the periodic Schur measure. When you consider, so instead of Schur polynomials, you should consider Schur polynomials evaluated at special numbers, which will depend on A, alpha, something like that.
And the Q is the same Q?
The Q is the same.
The same Q.
Okay, so we have this identity, and we are going to use this identity to derive a large deviation principle. First, how do we do it? First, let's consider the left-hand side. So the left-hand side is a probability of a sum of random variable, but when we can express this probability as the sum, well, there will be two components, one caused by the height function, and one caused by this additional random shift, independent random shift. But since we have already claimed in our heuristic argument that the tails decay with n squared, e to the n squared, it is quick to realize that the only variable, the only random variable that can contribute non-trivially to the limit here is the one with Gaussian tails. And so in this limit, we see that assuming that the large deviation, that the height function actually satisfies a large deviation principles, we can express this probability by scaling s as n times y. We can express this probability as e to the minus n times the infimum of two contributions, the rate function of the height function h and the rate function of a Gaussian, which is nothing but a parabola. So assuming the existence of the rate function, we can approximate this quantity here in this way. The operation of taking the infimum of two functions has a name in convex analysis, and it's called infimal convolution.
What is T in the yellow box?
It's a typo. N, should be N. The infimal convolution between functions and a parabola is actually, I recently learned that it's actually common in transport, optimal transport, as it is common in optimal transport to consider infimal convolutions with parabola in particular. So we have taken the limit of the left-hand side. Let's also consider the limit of the right-hand side. The limit of an expectation, an expectation can be expanded as the sum over all of the possible allowed state times the probability that such a state takes place times the value of the observable at that state. And so this is what we did here. So this is a big sum. In this big sum, this is a big sum of powers, products, triangular products. but we can approximate this big sum, especially if we care about the leading term, through a Laplace type argument with the maximal value. So we can approximate this expectation with the exponential of minus n squared times a certain function f alpha, which f alpha was given before, but you can recover f alpha from this expression by basically taking the 1 over n squared, the logarithm of what you see inside. Products will turn into integral, products will turn into sums will turn into integrals, triangular product will become double integrals, and this term here is going to become the linear potential that we have seen before. So, assuming that the rate function exists, we reach such an expression. The lower tail rate function of the stochastic 6-vertex model, when we take it, its infimal convolution with a parabola, needs to be equal to the functional f alpha, which is explicitly derived from this expression.
May I ask a question? So you have a discrete, maybe you said it, you need to rescale the L's to go to the large N limit?
Yes, there are several, you have to rescale all of the L's, exactly. You have to compactify, otherwise they escape to infinity, so you have to...
They are order N or something?
They occupy a portion of the lattice of size N, so you have to rescale.
Behavior is just like in random matrices, right? Yeah.
Yes. So, assuming that the lower tail rate function exists, we recover this explicit relation, and this explicit relation can actually be solved. You can imagine that now phi is a variable that you want to determine, is a function, but you want to determine this function based on this relation. Well, we are out of luck momentarily because this relation admits a unique solution phi only under the hypothesis that phi is proper convex and closed and convex. Proper and closed is something trivial, but convex is a non-trivial property. The convexity of rate function, in fact, is something rather tricky to establish in general. But in case we had convexity, then we could resolve this equation by this formula. You can find this formula in classical books of convex analysis, such as Rockefeller. So basically, what we are left to prove is that the rate function is convex and that it exists. But actually, if we think about what we did before, we proved before that the density, okay, the probability mass function, okay, we actually considered the tail before, but the probability mass function is asymptotically logarithmically concave. And in fact, this weak log concavity that I proved before is enough to establish that any potential rate function needs to be convex. So what we are left, we have proven some asymptotic convexity, we have proven a potential relation with log gases. We need to close the circle and say that the rate function exists and it is unique. And for this, there is something that we call the inverse Varadan-like lemma. Actually, we didn't come up with the name. Dembo heard about our paper and he said this thing, so I just decided to call it the inverse Varadan-like lemma. The Varadan lemma tells you that allows you to recover large deviation principle after you know functionals after you know large classes of functionals of your process. But in this case, we only know one function of our process, which is the convolution with a parabola, which you see here. So if you have a family of weakly logarithmically concave probability distribution, such that their convolution satisfies a large deviation principle, then this is enough to imply that the family of probability distribution, which was log concave, also has a large deviation principle, and its lower tail and its large deviation rate function is given by the infimal deconvolution between the rate function f of the larger process, the convolved process, minus a parabola. Yeah. So this is a theorem, but I have 0 seconds, so cannot be. It's something we use classical tools to prove this theorem, such as equicontinuity, proving equicontinuity properties of the pre-limit version of the rate function. But okay, maybe this is not the best crowd to submit my knowledge on Ascoli-Arzela. So let's move forward. So essentially what this theorem proves, this lemma here, proves that log concavity plus existence of rate function for convolved processes is enough to conclude the existence, to conclude the existence of and uniqueness of the lower tail rate function of the non-convolved process. Okay. So let me conclude. Okay, this is once again the statement of the theorem. So okay, let's read. A combination of integrable and non-integrable techniques has allowed us to derive lower tail large deviation principle. Integrable techniques came in with the connection with discrete log gas, the Meissner ensemble, and non-integrable techniques came in the argument to prove a priori convexity of the rate function. So actually obtaining explicit formulas should be challenging, because Riemann-Hilbert analysis of this problem shows multi-cut, shows that what is known to be equilibrium measure might be a multi-cut situation, might have saturated region, which makes the analysis difficult. Probably we need to invoke some deep knowledge of elliptic functions. Should be challenging, but maybe it's certainly things to think about. So the argument that I provided for the weak logarithmic concavity is quite robust. You can use it to prove a priori convexity for rate function of arbitrary growth, rather general growth processes, including higher dimensions. Or for example, you can prove that the marginals of the 6-vertex model, not the stochastic 6-vertex, the 6-vertex model, for example, the model discussed by Philippe, they are themselves log concave. And one thing that I already commented on is that the log concavity bounds are not sharp. There are error terms. But in fact, from numerical exact experiments, I have never been able to disprove the pure logarithmic concavity of the probability distribution of the height function, which, given the connection between the 6-vertex model and whole Littlewood polynomials, would imply logarithmic concavity of the whole Littlewood polynomials. If you know some articles, so for example, one famous article on so this article, when they prove log concavity of symmetric functions, are usually highly regarded, and this so far falls beyond what is available in literature, but it appears that this is logarithmically concave. Okay, I just maybe want to conclude here. Thank you very much.
Much. So is there any questions or comments?
About our future directions, can you also study the case with different initial conditions, like flat or stationary?
So what is interesting is that bounds, such as convexity bounds, should hold also in that situation. To study large deviation for different initial conditions, what I would do is I would use some polymer-like interpretation of these growth processes. So you can write the probability distribution of you can write the probability distribution at a certain time as the supremum over a certain classes of initial conditions. So I don't remember what is this formula called. This how would you write the probability distribution of the KPC equation with arbitrary initial condition in terms of the probability distribution of the KPC equation with droplet initial condition? The supremum formula.
Right,
I don't know what it's called. Anyway, I would do that. And so you add to this rate function an additional supremum.
For the flat case, you mean?
Yeah, for other initial conditions.
For the stationary case, or maybe two density case, maybe you can apply very similar techniques, or would it be already difficult?
So the problem is that, like I said, there was a recent paper by Varadhan and Setsuraman, where they proved the lower tail rate function, where they studied the lower tail rate function of ASEP with Bernoulli initial conditions. In that case, the lower tail rate function is in a certain sense less interesting because the upper and the lower tail have similar decay. They both decay like e to the minus n. The reason is that being the initial condition random, to create a lower tail event, basically you have to create, the way it happens is that you create a large gap in the initial conditions, and then that's how it happens.
But so this is real stationary case, right? What about the case, two densities, rho minus, rho plus? That would be pretty similar to.
In that case, I actually haven't thought about it, but I don't know. I believe that it's possible that it's still O of n. The decay is O of n and not O of n squared. But I don't know.
In the limit of 1, 0, this should reduce to this case, right?
But the rate function, I mean, it's like saying Bernoulli with parameter rho, where rho tends to 1. They still satisfy large deviation principles, which are the large deviation principle of a constant. So the randomness is important. You should rescale, in order to obtain something like this, you should rescale the density in a non-trivial way. So, okay, maybe we...
Okay, thank you.
Anyway, the bottom line is that I believe that even with any arbitrary, with Bernoulli density, stationary or not, the decay of the rate function is not like in this case. It's of order n rather than n squared.
So but are you saying that this particular behavior n squared appears only for the droplet in step case?
No, it needs to be deterministic initial condition.
It needs to be deterministic.
Okay. Oh, okay. Other quick questions? Okay, so
you said about your large deviation function phi. Okay, you gave properties, and then you say it's determined by your convolution, etc., in terms of log gas, where the potential is not regular. But what do you know about the regularity of the function phi itself?
That's interesting. So the function f is C1, but not C2. How do I know this? Because f can be written as in this way. Sorry, f can be written in this way. And it's a theorem from convex analysis that if you have a convex function, if you have the infimal convolution between a convex function and a parabola, this function is going to be C1. It's the convex analysis analog of the fact that any function convolved with a Gaussian is smooth. But in convex analysis, you don't have smoothness. You can always only get C1 property. The reason why it's not C2 is a bit more deep, but it relates to the fact that at some point it becomes a parabola. And if it was C2, it should stay a parabola, but this rate function connects to a parabola in a non-C2 way. Oh.
Okay. So let's thanks to speaker again.